this is Captain Chaudhary. Today I'm going to speak about high latitude navigation. What is high latitude navigation? You and I, we have been always, most of the times we have been navigating in navigable latitudes, say up to 60 degrees north latitude. But what happens when we go to higher latitude, say beyond 70 degrees north? So we will try to see what are the difficulties, what are the problems in respect of high latitude navigation. Well, there are various problems in respect of high latitude navigation. Let us analyze the problem in respect of, the charts which are there. What are the problems with the charts? Then let us look at the problems in respect of the terrestrial navigation. And then let us look at the problems in respect of celestial navigation. Then, of course, there are problems with respect to magnetic compass and the problems with respect to gyro. Now, in this part of lecturing, I'll be talking about these problems, but there are several other issues. Say, for example, polar code, the equipment, the instruments which we must have, that I will be doing in my second part. There are several problems as far as the charts is concerned. First, we will talk about the survey. Sometimes the charts are based on incomplete survey, as the survey had to be abandoned sometimes because of the bad weather. The survey provides the general outline of the land, not same as the outline we find on the navigational chart. We may not identify the land outline on the radar screen. That means they might be different. Moreover, when you surveyed the place, probably the ice limit was different, ice accretion on the land was different, and when you went there you found that the coastline does not match at all. Sometimes it is based on aerial pictures, and sometimes the charts are based on the information that is provided by the people who went there. So these are the problems as far as the survey is concerned. Another thing is, that means you and I, when we use the chart, we are used to the principle of Mercator projection, where the meridians are parallel and the distance. For example, if I want to measure north-south distance, I go to the side and measure it. Even if I want east-west distance or distance in any direction, I can find out the distance from the adjacent scale. So that is the ease I have on Mercator chart. These meridians are parallel to each other, so even if there is a single compass rose on the chart, I can use that compass rose. I can move the parallel ruler from one place to the other place, and that is the ease on the Mercator chart. But these Mercator charts don't help you in very high latitude because the distortion becomes extremely high. In fact, the polar regions cannot be represented at all, because the distortion of a polar area would be close to infinite. Okay, so this is a problem. On the high latitude charts, the meridians may not be parallel to each other, and if you want to find out what is the distance, you may have to use a separate scale rather than coming on the side and using the latitude scale. There are several other problems with the high latitude charts. Say, for example, you have land here and then land mass here, and this is the sea area. You may have chart for this area, you may have chart for this area, but those areas which are crucial for navigation, those areas which need higher details, those areas which need large scale chart, you may not have the charts for those areas at all. The charts may not be overlapping, as you see in the navigational latitudes. You normally have the charts overlapping in the coastal areas. Such things may not be found in high latitudes. Then the soundings which are given are for certain specific areas. It does not mean that the other areas are deeper. It means that the sounding was taken only for these points. So soundings are scanty, and you cannot navigate with the confidence that there is deep water otherwise. So what you need to do is you need to extensively use radar and the echo sounder. Echo sounder has to be kept continuously on, probably at slow speed. The problems in respect of terrestrial navigation. In the high latitude charts, you can see that there is no compass rose, and you can see that the meridians are not parallel to each other. So you have to use your protractor to find out what is the direction, what is the bearing, etc. So for this segment, right, I may have to consider the course as the course indicated by the mid position or the meridian at the mid position. Same way, if this is my DR and there is a lighthouse over here, I take a bearing, and suppose the bearing is 020, I need to measure that angle 020 from here, and thereafter I may have to pass that line through the lighthouse to get the position line. So these are the problems in measuring the courses, measuring the bearings. We have to compromise with the accuracy, and that is what it is. In fact, actually visual navigation might be considered better. Let us now try and understand the relationship between the grid course and course to steer. Let us assume a chart, say where the central meridian is Greenwich meridian, and here is a course to steer. You find that the course to steer changes every now and then. Very frequently the course to steer is changing. Now let us try and understand what is the grid course. If I draw lines, you find that the course to steer with respect to grid is always constant. Course to steer with respect to grid is always constant. In fact, at the Greenwich meridian, the grid course and course to steer are same. But on this side of the Greenwich meridian, that is on the west of the Greenwich meridian, you will find that the course to steer is less than grid course, and on the right side, that is the east of Greenwich meridian, you will find that the course to steer is more than the grid course. Course to steer is more than the grid course. So there is a certain relationship between the grid course and course to steer that can be found. If you are on west side, if you are on the west side, the course to steer is less. If you are on the east side, the course to steer is more. So suppose a grid course is G, right? If you are on the westerly longitude, what happens is you will subtract something, right? Minus something. So how much you have to subtract, that depends on the d long multiplied by the constant which is used on the chart. Same way, if you are on the east side, then course to steer is equal to grid course plus d long east into the constant that is used on the chart. So this way actually we are steering a steady grid course, but course to steer can be found if we know the constant that is used on the chart and we know how much are we away from Greenwich meridian, what is the d long with respect to Greenwich meridian. Then the other problems in respect of terrestrial navigation could be visibility, could be the presence of ice, could be a difficulty in the navigation otherwise. But when we talk about the terrestrial navigation, we need to be extremely careful in respect of the depth. We don't know, it's an unknown area, you might be navigating for the first time over that area. So depths are the most important concern. Now the charts are not conformal. The charts may not be conformal. When the survey, as I said earlier, when the survey was done, the coastline was different, and now the coastline is different. For all you know, The earlier what you thought was a mass of land, actually it was an iceberg, and that was not found when you navigated there. Celestial navigation. Let us try and understand the problem of celestial navigation, with the help of observer's rational horizon diagram. Let us say we talk about a high latitude, something like 70 degrees north, which means that on an observer's rational horizon diagram, the equinoctial appears here. This is observer's zenith, and we have the sun making a giant circle in the sky, and that is the path traced by sun. And we find that in this position the sun is very close to horizon, and in this position sun is very close to zenith. We have continuous daylight, right? So in this situation, when the altitude of the sun is say more than 15 degrees, we can take the sight. But once again, you will realize that although there is change of altitude, change of azimuth is rather faster compared to change of altitude. Let's take another situation where you as an observer are at North Pole. Then what happens? This observer's rational horizon and the equinoctial, they synchronize. And if you have the declination of sun, say about 7 degrees north, so you will continuously find the sun to be at an altitude of 7 degrees. Now you find that the sun is continuously very close to horizon, say 6 or 7 degrees above the horizon. You can't take sight because there will be error, because you want that the altitude of the heavenly body be at least 15 degrees so that the refraction correction is low or is predictable. Now here the refraction corrections are going to be very high and may not be accurately predicted. So it makes the situation unsuitable for taking the solar sight. Probably if the sun's declination is between 15 and 23 degrees, it makes the situation very suitable for taking solar sight. On the other hand, if the sun's declination is say 6 degrees south, so continuously the sun is going to be 6 degrees below the observer's rational horizon, it is going to make the situation difficult because you can't see the sun on one side, and the star sight cannot be taken, because although you have bright horizon, you may have bright horizon, but the stars are not visible because sun is very close to the observer's rational horizon. When you want to take the sun sight, there is no problem, you just need a clear horizon. So if you are spared by bad visibility or fog, etc., probably you can take the sun sight. If you are on the pole, say for example, you are very close to pole or you are nearly on pole, and the declination of the sun is say 10 degrees south. The sun is traveling along, you will never see the sun. Suppose you want to take a sun sight, and hypothetically say you are very close to pole, or let us understand that you are on pole itself. For the sights, it is desired that the altitude of the heavenly body, say when you are taking the sight of sun, the declination should be at least 15 degrees, because when the altitude is less than 15 degrees, the refraction correction may be highly exaggerated, they might be not reliable. So that leaves you with the opportunity of taking sun sight when the declination of the sun is 15 degrees north to 23.5 degrees north. So that's the limitation. Now, when you're taking the altitude, typically you must have seen somebody is reading the chronometer, somebody is taking the sight. So it is very important that the accurate time is used for, getting the accurate altitude for the calculation. But here, if you are, say, at pole itself, then the altitude of the body will remain nearly constant. So suppose you are exactly at pole, the declination of the star will not change at all. And sun's declination will change very, very slowly, which you will not realize. So in general, suppose you are in high latitude, you will find a very small change of altitude taking place. Basically, what is changing is the azimuth. If you have at all taken a sight, you can have a good angle of cut and get a running fix of position lines. Talking about the stars, stars need a twilight where the horizon is reasonably clear and the stars are barely visible. Now this would happen only when the sun is considerably below the horizon. But considering the situation that the altitude of the sun changes very slowly, there might be a situation for a twilight which is more than say what is seen in civil twilight situation. That means your horizon might be very bright, but the stars are not visible. So whether it is a good situation or a bad situation for taking sight, it is prolonged for a very long period of time. That is a problem with celestial navigation. And then when horizon is not visible, how to take the sight? So sometimes they say that in olden times they had to stop the vessel, they had to go on the ice, fix up the tripod there and take the sight with a bubble sextant angle. Bubble sextant angle means there is a bubble chamber where you have a bubble which is a reference for taking the sight and you get the object in the bubble. So bubble sextant angle is one of the methods of taking the sight when say the horizon is not there, and sometimes it will take you ashore on the ice when the ship is rolling. Other method of taking the sun sight is using the Mercury in a tray. Now this tray has got Mercury where you will see the reflected image of the sun and you get the angle between the sun and the reflected image. Of course you take the sight with normal sextant, but you need to place the Mercury once again on a tranquil platform. So when you take the sight, Mercury level should be like glass, So you might have a prism shape equipment where the sights are made up of glass, and you see the reflection of the sun through the glass. Now, talking about the magnetic compass. As you know, the magnetic pole are not at the same place as geographic pole. These are the geographic pole. Magnetic pole may be in say in 70 degrees north and south. So when we are close to the magnetic pole, what happens? Say this is the magnetic equator. You have the horizontal component and you have the vertical component of the magnetic compass. Now at magnetic equator you practically do not have a vertical component. You only have horizontal component, and horizontal component of the magnetic field is responsible for providing you directive force. Now these forces, these directive forces, they tend to become weaker and weaker as you go towards the pole. In fact, in addition to the pole, you might have numerous secondary poles. At magnetic pole or these secondary poles, what happens is the Z component is maximum and H tends to become 0. And because there is no horizontal component, we say that this is magnetic. Basically, total unpredictability of the performance of magnetic compass. So if we consider the field intensity, and we say that the magnetic field intensity, if it becomes less than 0.09 Oersted, the reliability of the magnetic compass becomes low. If it is less than 0.06 Oersted, then the magnetic compass behaves erratic, and if it becomes 0.03 magnetic intensity, then the magnetic compass cannot be used. It is useless after that. So there is this problem that will be faced close to magnetic pole. Other problem in respect of the magnetic compass is, when you are close to the magnetic pole, the distance between the isogonic line is very small, which means the variation would change very rapidly. Also, I told you the horizontal component of the magnetic field is very weak, so you need to keep a continuous check on your deviation. You need to take compass error very frequently. As I told you, the problem is in respect of variation as well as deviation. Now talking about the problems in respect of gyro compass. Now gyro compass can be used with reasonable reliability up to 70 degrees north, but thereafter the performance of gyro once again keeps going down. Let us try to understand the principle of gyro in a philosophical way. The axle, which is free in space, should follow the star, which means that a star that changes the altitude and azimuth is registered with this axle which is fixed in the space. Now the change of altitude and azimuth is because of rotation of the earth. That means looking at the change of altitude and azimuth, we can find out which way the earth is spinning. That is how a gyro function. Once the gyro knows what is the direction of earth's rotation, gyro will also be able to tell you a perpendicular direction, that is the north. So the earth's rotational speed is most important. Earth's rotational speed is maximum at, the east-west speed is maximum at the equator, and the speed keeps going down as you go towards the pole, and we may say that at pole there is no east-west speed. So now east-west speed of the earth is in a way providing the power to the directive force. Now this directive force becomes weaker and weaker as you go north. If we look at the errors in gyro, mechanical gyro, the damping error is rho tan latitude into 57.2. Tan latitude means it is sine latitude upon cos latitude. In a way, we say that the damping error is inversely proportional to the cosine of latitude. And what is cos of 90? Cos of 90 is 0, and 1 upon 0 is infinity. So this is what we find, that the damping error can become very, very high in high latitudes. Second error is north-south speed error, and north-south speed error, if it is delta, then tan delta is equal to V cos course upon 902.5 cos L plus minus V sine course. Now this plus minus V sine course can be neglected, and if we concentrate on this part, we can say that the north-south speed error is inversely proportional once again to the cos latitude, which means that these errors can be very high. The first error, that is the damping error in the gyros which are damped in tilt, and second error, that is the north-south speed error, they tend to become very high in high latitude. Even the ballistic deflection error can be also very high. On one side, these errors tend to become very high. On the other side, because directive force is weak, directive force is not all that strong, the correction of the error becomes difficult also. So can we say practically, beyond 80 degrees the gyros become extremely unreliable, and beyond 85 degrees no gyro can be used at all. Sometimes they talk about directional gyro. So there was this gyro Arma Brown which had a provision of doing some modifications whereby axle was set in a particular azimuth, and on that azimuth whatever were the horizontal and vertical acceleration, that means rate of drifting and rate of tilting, similar and opposite forces were provided to the axle so that the axle will remain fixed in that azimuth. Arma Brown gyro, after modification, it was not anymore the north-seeking gyro, it became the directional gyro. It shows the direction, but from time to time you need to check the accuracy of that direction. Now, what kind of features you want in a high latitude chart? Number one is conformality. Conformal means orthomorphic. It means that the scale all around a point is constant. Whether you want to measure the north-south dimensions of a lake or east-west dimensions, the scale is same, like how we find in the Mercator chart. So conformality is one very important feature that you are looking for. Number two, I would like to have the meridians a straight line, because meridians are going to decide the course, they are going to decide the bearing, etc. I don't want the meridians to be curvilinear. The third thing is the great circles, as far as possible, should be straight line. On these charts, I would prefer that the boundaries of these charts, they must look into, what the navigator wants in that area, not random. And then I want the charts in crucial areas. Charts in crucial areas, preferably they should be overlapping, and you should have large scale charts available for these areas. So these are some of the features I'm looking for in high latitude charts. The charts which can be used in high latitude are number one, transverse Mercator. As we understand, the normal Mercator projection this way, when a cylinder is tangent to the equator, so accuracy is maximum at the equator. In transverse Mercator projection, what happens is the tangency is on the meridian and inferior meridian. So these areas close to the meridian, they are very accurate, and they're basically used for survey, etc. And the distances may be shown in meters, kilometer, etc. The transverse Mercator projection, stereographic projection. Then sometimes mnemonic projections, Lambert's conformal projection. Now, a simple way to understand this is by photo and shadow method. Stereographic projection means, like, assume that there is a transparent globe, and say we are talking about polar stereographic, whereas the tangent plane can be on the side, when it would be called oblique stereographic. Now, source of light is on the opposite side of tangent area. Now this is tangency point, and we project the light from here, and whatever is the shadow caused on the sheet, that will be called stereographic, polar stereographic projection. We may sometimes use the mnemonic projection, in which case the source of light is in the center of the globe, and the graticules are projected on the plane sheet. Now this tangent sheet could be on some intermediate latitude, in which case it will be called oblique gnomonic, equatorial gnomonic. Wherever the tangent point is, the accuracy is maximum. So gnomonic projection, whatever area you want, you will have the tangency point there. Now talking about the Lambert's conformal projection. In Lambert's conformal projection, it is basically, it could be a two parallel standard conical projection. Like you have one parallel over here, you have another parallel over here, and let us say, just to understand it, source of light is over here. Everything that is projected between the two parallels and slight adjacent areas, what you get basically initially is the two standard conical projection. But if we adjust the distance between the parallels in such a way that the projection becomes orthomorphic, then it will be called Lambert's conformal projection. So what we have seen is, what are the ideal features I will be looking for in high latitude charts, and what are the projections which can be used in high latitude.